In this video, we will explain general equilibrium, how to write equilibrium expression, and what is equilibrium constant K. For a reaction, an equilibrium stage is reached when the concentration of products and the reactant remain constant. What that means is the reactant concentration decreases, and at certain time, the concentration is no longer changing during the reaction. Same way for the product, the concentration increases, and at certain time, the concentration of the product is also remaining same, but they are not equal. They are remaining same. So what's the reason for that is because the rate of forward reaction equals the rate of reverse reaction. How fast it is moving forward equal how fast it is moving backward. That's the reason the concentration at equilibrium is not changing for the reactant and product. Therefore, we call the chemical equilibrium is dynamic. That means it still keep going forward and reverse direction. And any chemical reaction in a closed vessel will reach equilibrium. Like we have explained in the evaporation. So what happened in the vapor pressure and the evaporation of water, we explained that in a closed container, when there is water vapor forming, at certain time, this how many water particles are changing into the vapor phase, same number of water particle water vapor will come down as liquid water. So that time, what is the vapor pressure here? That's what we defined vapor equilibrium vapor pressure. So that's the same concept, and this is physical equilibrium. This is physical equilibrium. The same way, we are explaining the chemical equilibrium and the characteristics of chemical equilibrium in this video. In a chemical equilibrium, we can quantify the relative concentrations of reactants and products at equilibrium with a quantity called equilibrium constant, which we represent by the letter K, uppercase K, which is written little italics K, and that is equal the concentration of the product. We can represent concentration in brackets, concentration of products divided by concentration of reactants. So this relationship between a chemical equation, balanced chemical equation, and the expression of this equilibrium constant, we call that one as law of mass action. Another example for a generic equation, we can write the equilibrium constant K by looking at the coefficients here. We have two products and two reactants. So equilibrium constant K, that small little c represent the concentration. We can write the concentration of product C to the power the coefficient L, and concentration of product D to the power M, which is the coefficient here, and concentration of reactant A to the power J, and concentration of reactant B to the power K. This Kc, you don't have to you don't have to write Kc all the time. That is same as simply writing K or Keq. So all are same. So normally we will just write K. That means it is C. That means it is representing the concentration of the reactants and products at equilibrium. So we will normally write just K, but Kc is same as K, which is same as Keq. And this bracket again, that's the concentration, and the unit we use for the concentration is moles per liter. That is nothing but molarity. While writing the K expression, we have to remember that we cannot put pure liquid and pure solid in the Kc or K expression. So for example, in this equation, we can see calcium carbonate, CaCO3 solid state, and calcium oxide is also in the solid state. So these are pure solid. We cannot show those two in this K expression. Only in this case, we will have only carbon dioxide because that is the only product we have in gaseous phase. So the Kc expression will be just CO2, concentration of CO2. Let us see some examples how to write the K expression here. The first one is H2 plus I2 gives 2HI. So what can we do here is we can write the K expression that equal product over reactant. So which are the products here? Only one product we have, that is HI, and we have a coefficient 2 that will be the exponent here, superscript, and we have two reactants. So I have to put two reactants, all are in gaseous phase. So I can take all, so I can write I2 here. And for the next one, I will see this is solid, this is gas, and this is gas. So we don't have to write this one. So I can just write K expression, again products over reactants that equal concentration of ammonia. I don't have any coefficient, it is balanced. So I have to just put these two. And the third one, I can say solid here, so I don't need this, solid, I don't need this, and I have two gases product. So concentration of AS4 and concentration of CO to the power 6. Next one also the same way, solid, I don't need it, solid, I don't need it. So K equal concentration of CO2 to the power 2 because I have a coefficient 2 here, and CO to the power 2. And in the next case, solid, I don't need it. Solid, I don't need it for the K expression. So equal concentration CO2 and no coefficient. It is all are balanced equations, right? All right. Now what we will do, we will try to plug in the numbers with the real concentrations for the reaction mixture. So let us see this question. Consider the reaction 2NOCl gas gives 2NO gas plus Cl2 gas at 35 degrees Celsius. Various amounts of NOCl gas, NO gas, and Cl2 gas are mixed in a 10-liter flask. After the system has reached equilibrium, the concentrations are observed to be chlorine 1.52 times 10 to the power negative 1 molar, NO 4 times 10 to the power negative 3 molar, NOCl 3.96 times 10 to the power negative 1 molar. So what we have to do is calculate the value of K for this system at 35 degrees Celsius. So what we will do first, we will write the K expression. So we have NO and coefficient 2. So we have to put to the power 2 and concentration of chlorine. And then we will write concentration of the reactant NOCl, and we have a coefficient 2. And just plug in the numbers. When you plug in the numbers, you can see that 4 times 10 to the power negative 3 for NO, and we had to put a superscript 2, and time 1.52 10 to the power negative 1 Cl2, and then for the reactant we will put, and also we have to put a 2 superscript. So these are the equilibrium concentrations. And now we will just simplify that. When you simplify, you will get 1.55 times 10 to the power negative 5. So when you plug in the calculator, normally what I will do, I will not put that exponent and also put in the calculator each one separate. Don't put everything together because it can make mess up with the number. So what normally I do for, I'll just take the numbers 3.96 since this is square, and here also square, and then the exponent I will take. So exponent 3 times 2 will be 6, right? So 10 to the power negative 6 and times 10 to the times means we have to add. So what we will do here is plus negative 1, and I have 1 time 2, so 10 to the power negative 2 at the denominator. So what I can do here is 1.52 divided by 3.96 times 3.96. We can get 15.68 times 10 to the power. It will be negative 7, and this is in the denominator negative 2, so minus 2, right? So that will be 16 times 1.52. So I will do step by step like that. It's always a good idea instead of putting everything together. So 15.68 times 10 to the power negative 7 plus 2. So that equal 24.32 divided by 15.68. I'll get 1.55 here, and times 10 to the power negative 7 plus 2 is negative 5. So let's try one more question. You can try this one and then check your answer. So here it will be the following equilibrium concentrations were observed for the Haber process, formation of ammonia from nitrogen and hydrogen at 127 degrees Celsius. So what we have to do, they have given the equilibrium concentration. So first I have to have a balanced equation. So for the balanced equation, it is forming from nitrogen and hydrogen, and we are getting ammonia. So when you balance, you can see that you can put 3 coefficient in front of hydrogen and 2 as the coefficient in front of ammonia, and we have the concentrations given. This is 3.1 times 10 to the power negative 2, and for nitrogen it is 8.5 times 10 to the power negative 1, and hydrogen 3.1 times 10 to the power negative 3. So first I have to write the K expression, that is products over reactant. So product ammonia NH3 to the power 2 because coefficient 2, and divided by concentration of nitrogen and concentration of hydrogen to the power 3. And now just plug in the numbers. For ammonia it is 3.1 times 10 to the power negative 2 to the power 2 divided by concentration of nitrogen is 8.5 times 10 to the power negative 1, and for hydrogen it is 3.1 times 10 to the power negative 3 to the power 3. So we can expand this one, or we can plug it in the calculator, whichever the way is easy for you. 3.1 to the power 2. So I will just put 3.1 times 3.1, and 2 times 2 is 10 to the power negative 4. That's the exponential rule. Divided by, this is 8.5 times 10 to the power negative 1 means it is 0.85 times, I have 3 times 3.1 because it is to the power 3, and 10 to the power 3 times 3 is 9. So I can actually cancel 3.1, 3.1, 3.1 and 3.1, that equal 10 to the power negative 4 divided by 0.85 times 3.1 times 10 to the power negative 9. So what I will do, 1 divided by 0.85 times 3.1. There is nothing wrong if you are putting everything in the calculator, whichever the way easy for you. So minus of minus 9 it will be. So you can try the way you like, but 1 divided by, so 0.85 times 3.1, I'm getting 1 divided by 2.635 times 10 to the power 5, because negative 4 plus 9, that equal 1 divided by 2.635, that will be 0.3795 times 10 to the power 5. I am actually trying to write in scientific notation. So 3.79, I can write how many sig fig I need, 2 sig fig. So I can actually convert that one into 2 sig fig, 3.8 times 10 to the power 4, because I'm moving the decimal. So 5 minus 1, so it will be 10 to the power 4.